Welcome back to Physics 142 Online.
Having talked about the force that a magnetic field produces on a moving charge, let's track its motion when it's moving in the vicinity of a uniform magnetic field. So if we've got a region in space where there's a magnetic field pointing into the board and it's uniform, which means it's got the same direction and magnitude everywhere, let's imagine that we have a positive charge plus q moving to the right with a velocity v. And if that velocity has a constant magnitude, what will happen is we can find from the right-hand rule that the force, which is in the direction of qv cross b, will be upward if that charge is moving to the right. So the force is upward, and that would mean the particle begins to be deflected upward. So its velocity vector is rotated so that now it has a trajectory with a positive y component in addition to maintaining an x component. But then as it moves in a different direction, the force still remains perpendicular to the direction of motion. And so when that force stays constant and it's always directed perpendicular to the direction of motion, that has to be uniform circular motion. That's exactly what uniform circular motion is. Force always constant in magnitude and directed perpendicular to the trajectory. And so we can trace out, if we were to do this calculation, we could trace out a circular path that the charge would make. Now remember, this means the velocity has a constant magnitude and the magnetic field is uniform everywhere in this vicinity. And it also means that the charge has to be moving in a plane perpendicular to the magnetic field. We can work out the quantitative relationships between the charge, the velocity, and the radius of the orbit very simply. There's the same kind of a picture here with the magnetic field pointing into the page. The magnitude of F is qvb sine theta, and if v and b are perpendicular, qvb. Newton's second law requires, if this is the only force, that this force be equal to mv squared over r if the trajectory is circular motion. And so we can solve for r in that expression and get it in terms of the particle mass, the speed of the particle, its charge, and the magnetic field strength. And what's also useful to know, especially for certain kinds of applications of charges moving in circular motion when there's a magnetic field, is the period. The period is the time it would take for one complete orbit. So the period would be the circumference divided by the velocity. And this just comes from the definition of velocity when the velocity is constant. So we can substitute our expression for the radius into this equation for the period. 2 pi over v times mv over qb. Notice the velocity cancels out, and we get an expression for the period that only depends on the mass and charge of the particle and the magnetic field. And that period, again, does not depend on the velocity and therefore does not depend on the radius. So all orbiting charges that are moving perpendicular to an applied magnetic field will have the same period. And some of the applications of this kind of phenomenon make use of that fact, that the period does not depend on the velocity or on the radius of the orbit. So one more general case would be if the charge is not moving completely in a plane perpendicular to the magnetic field, but if it has a small velocity component along the direction of b, then if we looked at the axis, we would see the particle tracing out a circular path, but because it had some initial velocity along the direction of the magnetic field, then it would have that circular path being moved along the magnetic field direction, and the path would in fact be a helix. And so that's a common kind of path where the cross-section is still a circular cross-section, but there is some velocity along the direction of the magnetic field, and that velocity is not affected by the magnetic field, because if we put a velocity along the magnetic field direction and calculated the force on that component, we would find it to be 0. And here's, you'll see in the textbook some other applications of this phenomenon of charges in circular motion, but here's a quick illustration of one of the important ones that chemists use all the time when they're trying to identify the identity of unknown samples. Let's say you have a molecule or an atom that is produced in some kind of chemical process, and you don't know what it is and you want to identify it, what's done is to ionize that molecule or ionize that atom, which means removing an electron. So now you have a positive charge, and it could simply be one positive charge if you've removed only one electron, or it could be multiple charges. But in any case, then you have a simple circuit where that ion is emitted from its source, and it's accelerated through a potential difference, which is going to make that charge accelerate, and then it is projected into a region where there is a uniform magnetic field. So in this example, the charge is positive, the initial velocity is upward, the field is out of the page, and so V cross B would give us a force that is to the right. And so that's why the charge then is deflected and traces out a semicircular path and hits some kind of a detector at point P2. So if we can measure where the charged particle hits the detector, we can measure the distance, which would be equal to the diameter of its orbit, and that would give us the radius. So in this device, we will use the radius that the charge traces out in order to find its mass. We can measure the voltage of the ion source that accelerates the ions toward the field, and that will be a way of determining what the initial velocity is. We can measure the magnetic field strength if we know the charge on each atom, and then inside the spectrometer we can measure the radius of the orbit. From all of those quantities we can work backwards to find the mass of the particle. And so this is a very useful way of taking this phenomenon and employing it to measure the mass of an unknown particle. Now, I believe in class I alluded to the idea that if there is a closed current loop in the presence of a uniform magnetic field, there is no net force on it. And yet, a magnetic field does do something to that loop, and what we're going to do now is figure out how to calculate this torque that the magnetic field imparts to a closed current loop. The current loop is defined by an area, and of course it can have different shapes. It could be a circular loop, it could be a rectangular loop, as in this case, but the area will be the important quantity along with the current, and then the orientation of the loop. If the loop is indeed planar, and we'll focus our attention on that case, there will be a normal vector to the surface, and the normal vector then will always be able to tell us the orientation of this loop. So imagine a magnetic field B applied in the direction indicated in the sketch, and let's think about what the forces are on each of the four segments that make up this rectangular current loop. And it's pretty easy to see that there won't be any force on the lengths, the segments of wire, where the current is parallel to B, and that would be the side here on the left and then the side on the far right. However, there are forces on the sides A of length A, and those forces will be in different directions, although they will have the same magnitude. So let's sketch out what those forces are. From our equation of the force that a magnetic field produces on a current loop, we know that it's the integral of I dl cross B. So initially, even before the loop begins to rotate, we would find that those two initial forces would be the current times the magnetic field times the length A. And by the right-hand rule, we find these two forces F1 and F2, one pointing up and one pointing down. The two forces have the same magnitudes initially when the current loop begins to experience the magnetic field, so there's no net force. But the two forces act in opposite directions, and if this current loop is free to rotate, maybe it's connected to some sort of a rotation axis here, then the part that is experiencing force F2 will move upward, the part with F1 will move downward, and the entire loop will begin to rotate. And now as it rotates, there will become a net force will begin to be exerted on the two sides of the loop that have length B, but they will be equal and in opposite directions. And so they won't exert a torque about the axis that's indicated here. So if we want to find the torque, all we have to do in sort of a side view here is figure out that the forces F1 and F2 each produce a torque, and if the loop has rotated through an angle theta, so the normal vector now is an angle theta away from the applied magnetic field, then the torque, r cross f, we can write it as r perpendicular times f, and the perpendicular distance is b sine theta in this sketch, the perpendicular distance from the force to the axis of rotation. And so that torque will be I times the magnetic field times AB times sine theta. And where does this come from? We're just substituting in to the place of the force the expression that we found over here. And so what you see is this product A times B, which is the area of the loop, enters into the equation. And we won't derive this sort of equation for a circular current loop, but it turns out to have the same property, that if this loop were circular or ellipsoidal, the torque would always be the current times the field times the cross-sectional area, and then times the sine of this angle between the normal vector and the magnetic field direction. And what's nice for us to do is to condense this expression for the torque into a vector equation. And so if the cross-sectional area A has a vector n hat perpendicular to it, we can define this quantity here as I times A times n hat cross B, because the n hat and the B, if we take their cross product, we'll get this term sine of theta. And so this is just a very shorthand way of expressing the same torque that we calculated previously. And this torque in this problem, if you take n hat cross B, the torque is into the page, which means that the thumb in that direction defines then, by the rotation of the fingers around that thumb, it defines the sense of the rotation, which in the sketch above here will be in the clockwise direction. So we can also write this torque down in a slightly different way by just defining the magnetic dipole moment of the loop to be the current times the cross-sectional area, and then the vector nature of it is given by multiplying by the normal vector. So the torque becomes, which was in the previous equation, IA n hat cross B, we can summarize that as the torque being mu cross B, where mu, this definition, is the magnetic dipole moment. And hopefully you remember that when we talked about electric dipoles, we also defined something called the electric dipole moment, and that was a measure of how strongly that dipole would be affected by the presence of an electric field. Just like here, the larger the magnetic dipole moment, the larger the torque will be when a magnetic field is applied. And it's important here, if you think about the direction of this normal vector, when you've got a current loop, the normal vector could be either perpendicular upwards or downwards from the loop. So which way is it? Well, we define it so that it's consistent with the torque equation, so that if you take your fingers and rotate them around the current loop in the direction of the current, your thumb will point in the direction that's perpendicular to that loop, and that's the direction n hat, which is the direction of the magnetic dipole moment. So a lot to digest here, but I will just now point out some similarities between the case of a magnetic dipole moment in the presence of a magnetic field and the presence of an electric dipole moment in the presence of an electric field. So here, imagine that you've got this magnetic dipole moment, and I'm not drawing the current loop that gives rise to this, but just showing the orientation of the dipole moment. And so if it's in the presence of a magnetic field, we know that the torque it's going to experience, in this case, would be in the clockwise direction. So that magnetic dipole moment will be given a torque that makes it want to line up with the magnetic field. And we can express that interaction in terms of a potential energy function. And we can write it down here. I won't derive this, but because there's a torque, we could calculate the work done by the magnetic field causing the dipole to rotate, and because of that work we can define a potential energy function. And it has the form minus mu dot B. The minus sign is in there because the lowest potential energy orientation will be when the moment mu is parallel to the magnetic field. So if you think of the mu as a compass needle, and you think of the magnetic field as being the magnetic field of the Earth, the compass needle wants to rotate to line up with the magnetic field direction. So that minus sign tells us that when mu and B are parallel, then the minus sign will make the potential energy as low as it can possibly be. And now I just want you to compare the two equations that we got when we talked about electric dipole moments in electric fields with these two new equations for magnetic dipole moments in magnetic fields. And the similarity is striking. A magnetic dipole moment is acted on by an electric field in exactly the same way that a magnetic dipole moment is acted upon by a magnetic field. So we'll leave this similarity here as something to ponder, but there's apparently a very deep connection between the influence of magnetic fields and the influence of electric fields. And this is why in 20th century physics it came to be known that the magnetic and the electric fields were just slightly different manifestations of something more general that we call electromagnetism, or the electromagnetic field. And so I will see you in class.